The ideal gas, we said, is an approximation of real gases where gas molecules take up zero volume and do not interact with each other. This approximation is valuable since it provides a simplified benchmark for behavior of real gases. It is a good approximation at low pressures where molecules are so far apart that they do not interact, nor are the molecular volumes significant. Hence, B over V, C over V square and higher terms in the virial equation of state are zero, because as P approaches 0 and V approaches infinity, the higher terms become insignificant. Thus, PV is equal to RT. For ideal gases, the internal energy is only a function of temperature as well. Now let's look at non-ideal gases at low pressures. Consider, for example, the compressibility factor Z as a function of P for methane. At minus 150 Fahrenheit, Z depends in this fashion with P, and then at a slightly higher temperature it does this, at a slightly higher temperature of 0 degrees Fahrenheit it does this, and then here, here and so on. So for all of these cases we can write Z is equal to B dash P plus C dash P square. So we can fit all of these graphs using a quadratic equation, 1 plus BP plus CP square. B dash and C dash would depend on the temperature, so I could fit this with the value of B dash and C dash, this with a different value of B dash and P dash, so B dash and P dash depend on temperature. Similarly, I could also fit Z as a function of volume, so I could represent Z with respect to volume, and I could fit an expression where Z is equal to 1 plus B over V, C over V square. Again, B and C would be dependent on temperature. The virial equation of state we saw is an infinite series, but for practical purposes it's useful only if the series converges quickly, which means that 2 or 3 terms of the series are good enough to represent the behavior of this material. So I could use 2 or 3 terms would be good enough for me to describe how Z would depend on P or Z would depend on V. We saw that at pressure equal to 0 or at extremely low values of pressure, Z is equal to 1 or PV is equal to RT is a good enough approximation, so we can use one term and that's good enough. At low to moderate pressures, that is close to pressure equal to 1, a two-term virial is a good approximation. So 1 plus B dash P or 1 plus B over V is a good enough approximation. Z is equal to 1 is not a good enough approximation and under these conditions, because at low to moderate pressures there is interaction between two bodies, two particles in the gas, and we begin to see that this ideal gas behavior is not true. At higher pressures we need cubic terms, because now three body interactions are also beginning to play a significant role. So I have Z is equal to 1 plus B over V plus C over V square, or Z is equal to 1 plus BP plus CP square. We find that for higher pressures, especially when we use this three-term model, Z is equal to 1 plus B over V plus C over V square is a more accurate form than when we express Z as a function of pressure. Again, we remember that B, C, B dash, C dash, etc. are functions of temperature. As pressure increased, 2 and 3 body terms began to become important. For example, with methane, we would need a quadratic expression of pressure and volume to appropriately define the behavior of this material. Clearly, a linear equation of pressure and volume was not enough. We see that a linear equation would form some kind of a straight line. That was not enough because you had these curves coming in, and hence you'd need a quadratic equation at the very least. We saw that virial equation using 3 terms was an example of a quadratic equation. You had Z is equal to 1 plus B dash P plus C dash P square.